So today we
Hey.
have Georg Lehner speaking on the map from K0 of ZG to K0 of QG for general groups.
Okay, well, first of all, thanks for letting me speak here. It's a nice opportunity to share some of my results. Yeah, the title says it all, basically. So if you know what all the objects involved are. So let's start with this. First, let's fix some notation. G will always be a discrete group. Sometimes people think of V groups as well, but in this talk we're focused on that. R will be a ring. We sort of think as the base ring. Do things over, and then RG will denote the group ring or the group algebra over R. So this is just formal linear combinations where you have coefficients AI in the ring, and you have GI in the group, sort of giving the basis elements, and the real are only finite sums. Okay, and this is in general a non-commutative algebra over R. It's commutative exactly when the group is abelian. And what we are interested in is a very classical invariant, is the K-theory group, the algebraic K-theory group of this group ring. And this zero here denotes that there's some higher algebra also going on, but let's come to that later. And the Y is because this group appears in a whole lot of different geometric problems as a natural abstraction. The most directly related one is Wall's finiteness criterion. So if I have a space X, then that is a CW complex. I could ask whether it's finitely dominated, whether there's a finite CW complex that covers it, such that it's basically such that it's a retract of it. And this is related to one element in this group, K0 of that integral group ring, vanishing, and this is called the Whitehead torsion. So this is sort of the earliest example of the K-theory group appearing, goes back to the 50s. The other important one is representation theory. And in representation theory, we care about irreducible representations. And if you look at K0 of the base ring being a field, then this has to do with the representation ring, if G is a finite ring. So you can think of this as a generalization of the representation thing, of the representation ring of a group. Okay, and of course you can always sort of go from the integers to the rationals by, if you have a set G module, you can tensor it. You get a QG module, and so this gives a natural map. I haven't defined yet what K0 is, but there is a natural map between them, and we will try to understand this. Okay, so what is it? What is K0 of R? So let P of R be the set of isomorphism classes of finitely generated projective R modules. You can do that. Then this is a commutative monoid with taking direct sum of projective modules as the addition. Okay. And then K0 of R is just defined as the group completion of this commutative monoid. It's also called the Grothendieck group. So to be more concrete, you can take the free group generated by the set PR, and then you mod out by relations that you enforce the addition to already be the direct sum on all those two elements that you could already add before. And now you, of course, you have added inverses, so this is now an abelian group. And as an example, you could take R to be the integers. It could be more generally be a partial. But yeah, let's just stick to the integers for now. So for the integers, every finitely generated projective module is free. This statement is also true for a PID. That's why it doesn't make a difference in arguing. So the set PR together with its abelian groups, if its abelian monoid structure is isomorphic to the natural numbers, therefore its group completion is isomorphic to the integers. Okay. And something similar happens for a different class of examples, which is if R is a field. Or it could be more generally a division algebra. Then if you go back to linear algebra, you've learned that every vector space has a basis. And so since it has a basis, it's a free module. So therefore, again, you get the integers for the case of a field division algebra. Okay, so those are sort of simple examples. Well, we'll come to more complex ones later. There's also a notion of reduced K-theory, which is if K-theory is sort of like a homology theory, then reduced K-theory is sort of like reduced homology. So you always have the inclusion of the free modules into the projective ones. That basically, as we've seen before, where we always reduce to the case of free modules. So you have a natural map from the integers into K0 of R. And you can think of this as being the map from K0 of C to K0 of R, basically giving the functionality of K0. And then you define this K0 tilde, K0 R tilde, to be the co-kernel of this. Okay. So essentially, if you had the integers of a field, then this group would be 0. Whoop. And if you now look at the case of a group ring or of a group algebra, then you can easily show that this is split. Essentially because the inclusion of the integers into the group ring is a retract. Because you can always sort of, if you take the group algebra and you send all non-trivial group elements besides the identity, basically, all of them to 0, and you send the identity to 1, that gives you a nice ring homomorphism. And yeah, and this means that this group here splits off. The same goes for a work field. And since basically then you'd have K0 of the integers sitting here, which is the integers, and also K0 of a field, which is also the integers, you have these nice splittings. So if we come back to the question that we were interested in, we had, remember, we looked at, we wanted to understand K0 of the integral group ring to the rational group ring. So we had this free part, and on this it's an isomorphism. If I send a free module to a free module, then this is exactly the identification. So we're left to understand this split summon, because this split is natural. So we're left to understand this with the twiddles on, the reduced K-theory. Okay. And there's a first theorem that I'm going to cite, which is not trivial to prove, but it's doable. And Swan proved this in the 70s, that if G is a finite group, then this group here is a finite abelian group, as in, yeah. In particular, it's torsion, which is highly relevant. As a slight warning here, this group can be really, really complicated. So for the case of a cyclic group, CP, this is related to the ideal class groups that pop up in number theory. And they have some really weird structure. So for all primes smaller than 19, this group is 0, okay? But then all sorts of strange stuff. Okay, for 23, it's a set mod 3. For C29, it's 3 copies of set mod 2. And then for 31, it's a set mod 9. And for 47, it's exactly set mod 37. And there's no apparent structure if you just look at the list of primes. So you can't really expect a nice formula to come up when you want to compute those groups. So it's more like case-by-case analysis. But if we look at the algebra over a field, the entire story is a little bit simpler. So let's quickly talk about representation theory. If we now fix a finite group and K a field, and the characteristic we assumed not to be of the order of G, then, or we assume that the characteristic doesn't divide the order of G. I think that's a slight typo here. Interesting. Then there's Maschke's theorem, which says that every representation, every finite dimensional representation, I should say, this is what I mean by representation, splits into irreducible summons. And this has some nice consequences for our case, because now, since all irreducible representations are split summons of the regular representation, it means that all representations which are built out of those irreducibles have to be projective, because they're just finite sums of projectors. So as a corollary, if we compute this group, the irreducible gives a basis of the K-theory group. So K0 of the group algebra over field is just free group with rank the number of irreducible G representations. Okay. So now we can state a nice theorem. If a group is finite, then this map here is trivial. And why is that? Because, well, this group here is finite in particular torsion. This group here is free. So it has to be the zero map. That's why the quotation marks of theorem is here, because the proof is so simple. There's not really much to do. That's the fact that the groups on the left are finite, which is, not trivial. But. So the question that I want to ask is, can we generalize this? So for example, if I just take the group SL2 over the integers, the sort of cover of the modular group, which is a very natural example to consider, right? It pops up in math everywhere. Then what is this map? Can we say anything from those results? Now, there are some problems. Basically, in the 90s, Kropholler, Moselle, and then 1 year later, Leary, and they've constructed groups that are not too complicated to write down, but they have naturally two torsion in K0 of the rational grouping. So we cannot use this argument that the codomain is a free group. So this just
Sorry, is torsion in K0 or in reduced K0?
Oh yes, in reduced K. Well, in this case, if the integers are a split summand of this, and you get reduced K-theory, but taking away the split summand, then
oh yeah, that's a good point.
The torsion still has to be in the split summand. So that argument also works. But yes, thanks for the question. Yeah. Okay, so my tool of choice is something that has had a lot of progress happening in the last 10 years, which is work on the Farrell-Jones conjecture. The bottom line is that the Farrell-Jones conjecture allows you to compute the K-theory groups of an arbitrary group, if it satisfies the Farrell-Jones conjecture, from simple building blocks, namely the K-theory groups K of RH for H being a virtually cyclic subgroup. And virtually cyclic is it's a bit more complicated than finite, but it's not too bad. So the definition of virtually cyclic is that there exists a cyclic subgroup of finite index. And at first you might think, well, that can still be quite general. This happens only in free classes of groups. And of course, H could be finite. Or it fits into a short exact sequence where you have the integers on the right. So you project onto the integers. And the kernel of this map is finite. Or you project onto a group that is isomorphic to the infinite dihedral group. Let me quickly, for those that don't know, the infinite dihedral group is isomorphic to a free product of the cyclic group with two elements of itself, or it's given as basically acting CMOD2 acting on set by where the conjugation sends an element to the inverse or to minus. Okay. And this is not too hard to show. I mean, it's a bit tricky, but like it's not a deep theorem or anything like this. So since you have those three classes of groups, arguing about virtually cyclic groups sort of always goes back into those three cases. Yeah. But there are some caveats here. So I only introduced a K-theory group, not a K-theory spectrum. And on top of that, we cannot just take connective K-theory, we have to go non-connective ones, so we have to have negative K-theory groups as well. And only then does Farrell-Jones conjecture work. So I have to introduce some terminology here. And this is sort of the caveat that I assume that you've seen something like stable infinity categories before. And if not, then just, I hope that you get the intuition behind it. This goes back to Thomas Nikolaus, he has had some really nice lectures recently that sort of try to introduce K-theory from the viewpoint of infinity categories, and then there's sort of some nice ways to think about things. So now define proj R. Remember we had this PR, this set of the isomorphism classes of projective finitely generated R modules before. Define this as the groupoid of finitely generated projective R modules. And the only morphisms are isomorphisms, otherwise you wouldn't have a groupoid. And this is what's called an E-infinity monoid. So you have an addition, can take the direct sum. But if you think about it, associativity laws for addition
Seems we lost you briefly.
My Zoom disconnected for a couple seconds. Unfortunately, it's just a couple of seconds. I was scared for a second. Okay. Sorry about that. I don't know what happened here. I hope you could hear me before. So you define connective K-theory as the group completion of this E-infinity monoid, and there's some deeper sort of results in the infinity category world in higher algebra, is that a group like a infinity monoid is the same thing as a spectrum. So there's a natural version that sort of generalizes the group completion of a cumulative monoid. And this is exactly this process. I won't go into this because after all, I have to state my results at some time, but I hope you can take this as a black box. So this is a spectrum, and it has a nice property that relates everything. If you take pi 0 of the spectrum, you just get K0 back. Okay, so this is good. And then we can define higher algebraic K groups via, well, just take the higher homotopicals of this spectrum. So now I still have to define non-connective, whoops, it's a bit twisted, but it's okay. Non-connective K. Sorry, I told you it's the first time I'm using this. So define the nil groups as you have your ring R, you have the natural inclusion in the polynomial ring, and you can look at K-theory. And then you take the cofiber of this. And with this in mind, there's a nice theorem. This is sort of the universal theorem, or the fundamental theorem of algebraic K-theory. It's often denoted as this is the Bus-Heller-Swan theorem, is that if you take K-theory of the Laurent polynomial ring, then it splits into 4 summands. And one of them is just given by the inclusion of the ring R into the Laurent polynomials. That's this part. And then there's 2 times the nil appearing. And that is basically because you can take the polynomial ring and you can sort of include it once via the variable t, but also once via the variable t inverse. And then there's a 4th term appearing, which is going to be a suspension of a spectrum that almost looks like K-theory, but it has an additional term in degree -1. So this K greater than or equal -1 of R is going to be a connective cover of K greater than or equal 0 of R. And using this machinery, one can basically go by induction and then by applying Laurent polynomials in rings all over again. For n many times, you can define this term, this K greater than or equal -n of R. And since we just want to have one object and not n many objects, we define the K-theory spectrum, the non-connective K-theory spectrum, to be the co-limit over this. So basically every time you do this process, you just add one further homotopy group one level down. Okay. Okay, this is very abstract, I know. It only makes sense if you've seen a couple of examples, but in our case, it's not too bad. So there's some nice properties of rings that let you sort of forget all this negative stuff, and this is for being regular in Noetherian. And so this is, for example, the case for the integers or for K field or for the division algebra. And it's also true for the group algebra over the rationals. So this is not too hard to show, but I won't go into it too much. But you show that, well, this holds for the rational group algebra, so therefore all negative homotopy groups disappear. And what I just told you about non-connective K theory doesn't really, it is not really relevant for the rational group algebra. So in this case, we already get connective results. In the case of the integers as a base, this is a bit more complicated. So Carter proved this in 1980. And so if you have a finite group, I hope I said that this only works for a finite group, of course. Yeah. For a finite group, then the integral grouping has one negative homotopy group, one negative K-theory group, and this sort of only has the free group part and a set mod 2 part, a 2 torsion part. And those two coefficients are G and SG are, well, they're not too bad. RG is given as some linear combination of numbers of irreducible representations over different fields. Namely, you compute the number of irreducibles over the rationals, you compute the ones over the p-adics, over FP, and then you take exactly this sum here, and this gives you this rank. And what is more important for the rest of this talk is the following, which is this coefficient S of G here. And I won't go precisely into the details because it would require a little bit more setup. But this is given as the number of irreducible Q representations that have a global even Schur index. So they sort of behave like quaternion algebras. But if you p-localize, they don't anymore. So the p-local Schur index is odd. The Schur index sort of gives you, if you take your irreducible representation and you tensor it, say, with the complex numbers, how many times it will split up into different copies of an irreducible. And the p-local one is if you first p-localize it, and then this will split up into certain irreducibles. It has the property that each of those irreducible summands, when you then go to the complex numbers, still splits into the same number of different irreducibles. And that's the p-local Schur index. So in some sense, this has something to do with how quaternionic those are, but the quaternions themselves aren't fulfilling this property. It has to be a little bit more complex than that. So, and the last part about this theorem, which is super nice, is that further down, the negative K theory disappears for integral grouping. And this is great because then we only need to worry about anything that is above degree -1. Okay. So let's talk a little bit more about this condition for S. So if I is a rational representation that has even Schur index, but there's odd p-local Schur index everywhere for the p's. So there's a theorem that the rational Schur index is the greatest common divisor over all p-local Schur indices and over the real Schur index as well, which is a bit more well known. The real Schur index of a representation has to do with basically whether you can find a quaternionic representation that gives this real representation. And so this is also sometimes called a symplectic representation. So in particular, this can only happen if this is a symplectic representation, and this only happens for groups that have orders divisible by 4. And Carter showed in his paper that most groups, well, they don't have this. They don't, for most groups, you will have S equals 0. Most in the sense that all of the ones that you will immediately think of, unless you already know that you have to think of specific quaternionian groups. So symmetric dihedral abelian groups all will fall out. They don't have this property. And he moreover showed any group with a normal abelian subgroup of odd index. So, the smallest group that has non-trivial S is the group Q16. This is like the quaternion group, like group Q8, except as a generator of this, you just take e to the pi over 4i, not pi over 2i. And you can look at this in the unit quaternions, the subgroup generator that has 16 elements. And this group has exactly S is equal to 1. So, and then much later in 2013, McGurn computed basically the negative K-theory of a wide range of finite subgroups, namely finite groups that have quaternionic nature, namely those finite subgroups of SU2. Yes, let me just write it on the side here. So, but this is S is equals to 1. Okay. Like you can actually compute that K minus 1 of set of Q16 is equal to set mod 2. So there's no free part. Okay. Oops. What's that here? So, and the finite subgroups have of SU2 have fall into basically 2 infinite families and then 3 sporadic cases, like with many things in math. And here, the groups, those are the cyclic groups. They're inverse images of the cyclic groups, and I think I made a mistake here. It has to be 2n. It has to be the inverse images of 2n, and then the sporadic cases here, I'll go in a second, of the double cover of SU2 on SO3. And the groups T here is the tetrahedral group, the symmetries of the tetrahedron. O is the octahedral group, symmetry groups of the octahedron, and I is for the icosahedron, the symmetry groups. So those are called binary tetrahedral, binary octahedral, and binary icosahedral groups. And the group dicyclic N, so if you plug in the value 4 here, you exactly get Q16 back. And what he computed is, well, I won't list all the values because they're sort of difficult to write down, but in general, if you look at K minus 1 of the dicyclic group, this is non-trivial for n greater than equal 4. And for the exceptional cases, he also computed the K-theory groups, which is in the tetrahedral case, you only have a free part, but for the octahedral and the icosahedral, you have to use 2 torsion parts. And I went through the trouble of doing some gap computations and sort of letting my computer run for a couple hours and then analyze the results, and all groups that have non-trivial S of order less than 100 are extensions of these. I don't know if it's true in general. There could be still some really big group that only embeds into some higher general linear group over quaternions and not just in the unit quaternions. I don't know yet, but definitely those are like the prime movers of when something has non-trivial S. Okay. So now let's get back to assembly and Farrell-Jones contractors. So basically, I went through all the trouble to talk about non-connective K-theory, the non-connective K-theory spectrum, sort of, so I can even phrase the Farrell-Jones contractor. So let's do that now. Now G is an arbitrary group, but it's not finite anymore. Then there's 3 categories that are relevant for us, which is the orbit category of G, which is just you look at G sets and then you take only those G sets that have transitive orbits, meaning they're isomorphic to G mod H for H a subgroup in G. And then you can define those sub categories by only allowing H to be virtually cyclic or H to be finite. And you can do this with any class of groups, of course, but those will be the three interesting ones for us. And there's a really important paper that Davis and Lick wrote in 98, which basically concerns with the constructions of a functor that on objects G mod H give you K-theory of the group ring with H as input. So you have to do some work here because like K-theory is only a functor basically in ring homomorphisms, but then conjugation and induction are not like you have more G maps than you could just get by ring homomorphisms. Anyhow, so we have this nice functor K of R, and as a note, in the orbit category, G mod G is just a point. So this is a terminal object. So if you compute the colimit over this functor, then you get the total group ring back. And assembly is basically saying, well, you don't need to have the entire colimit. Or rather, you could compute the colimit over smaller subfamilies. You can take the colimit over RG fin or the colimit over RG B cyclic. And then because those are so subgroups that are included in one another, there are natural maps that compare everything. And those are called assembly maps, with the total case being the entire group ring. Okay. And then there's also a really trivial case, but that's important sometimes. If you just take the colimit over the object G mod 0, which has exactly G as the automorphisms of it, then you get that the colimit over this is a BG plus smash KR. The reason for this is that on KR itself, the group action is trivial. So essentially you have a constant functor, and if you take a colimit over a constant functor of a category that is just a classifying category of a group, which means a single object and the automorphisms are given by the group elements, then what you do is you get just the realization of the group of this category, which is BG, and in this case, since we're in Spectre, you have to sort of take the plus and the smash product. So we have a natural map, which is called the trivial assembly, which goes from BG plus smash KR into K-theory of the group ring. And this is sort of my starting point for what the generalized version of reduced K-theory should be, because before we sort of split off a point, and now we split off an entire BG plus, which is the result of which is called the Whitehead spectrum. And really, in many of the geometric problems where K-theory appears, of K-theory of group rings, secretly the Whitehead spectrum is the one that you're actually interested in, because basically what's on the left here is almost sort of trivial, like that's what comes from KR as a homology theory. That's like that's what's nicely behaved. So you define the Whitehead spectrum as the co-fiber of this map, similar to how we define reduced K-theory as the co-kernel. And then it's not hard to show that this defines a functor on the orbit category, similar to K-theory. And well, if you compute the homotopy groups of this, because you have this fiber sequence, it's not really hard. The zeroth homotopy group is just reduced K-theory, and this is both in the integral as in the rational case. And the negative homotopy groups are just the negative homotopy groups of the, wait, this is with a caveat that I should add. Is equal to the integers or is equal to the rationals. No, it's not true in general, but for those two cases it is. Basically for any regular Noetherian ring this will be true, but yeah. And this map in pi 0 is exactly the map in reduced K-theory that we're interested in. So this is why we went through all this trouble to define this, because well, now you have a spectrum that has nice properties, relating to K-theory. So I'm almost done with this section. I'm sorry if this is very abstract to get through it. A functor satisfies a finite or virtually cyclic assembly if this assembly map is an isomorphism or an equivalence, whether it's an isomorphism on homotopy groups. So let me now state the Farrell-Jones conjecture, which is that G satisfies the Farrell-Jones conjecture if this K-theory functor satisfies virtually cyclic assembly. And this has been, there's been a lot of research happening in the last 5 years. And basically what was shown is that this Farrell-Jones conjecture holds for really wide category, class of groups, to the point where we have no counterexample right now. No proposed counterexample, nothing to consider. But of course, as with many things in group theory, if it's decently complex, then you cannot say things for every group. You have to sort of go by case analysis on different classes of groups. So it might still be false, but if it's false, then it's a really strange exotic group. Anyhow, so examples would be hyperbolic groups, cat-zero groups, solvable groups, lattices and almost connected Lie groups, fundamental groups of d-dimensional manifolds if d is greater than or equal to 5. I think I should add this here. And a lot of people that I've listed here, those are not all, have worked on this. So, and this is sort of why my starting point, like we have this really strong theorem for a lot of groups, like what can we do from this? And this is sort of why I was trying to think about something that's true for finite groups, like how could we generalize this? And okay, so, and if side remark, because we talked about the Whitehead spectrum before, like if G satisfies the Farrell-Jones conjecture, then this Whitehead functor satisfies assembly as well with respect to virtually the family of virtually cyclic groups. And this is basically the 5 lemma. You have those two fiber sequences of spectra. You have an equivalence here. It's the identity. If this is an equivalence, then this is. So it's if and only if, basically. Okay. And some consequences of the Farrell-Jones conjecture for the groups that we're interested in is, oops. If G satisfies the Farrell-Jones conjecture, then also the negative K-theory isn't too complicated, because then for all n greater than or equal to, there's for k minus 2 and lower, these groups will vanish for an integral group ring, and for the group rational group algebra will also vanish, but then for anything minus 1 and lower. Okay, we still need some nice theorems, which is, first of all, that if you look at the rational group algebra, then it already suffices to look at finite subgroups, because the assembly from finite to virtually cyclic group is already an equivalence. So if G satisfies the Farrell-Jones conjecture over the, then I only need to compute the finite, the K-theory of the finite subgroups of G. If I want to compute K-theory of over the rational grouping. So the rationals are sort of really easy behaved. And a nice theorem to do Bartels in 2003 was that this map now for any ring, base ring R, is always a split injection. And this is natural in the ring R. So if we put those two things together, oops. Then, so if we assume that G satisfies the Farrell-Jones conjecture, so as I said before, KG, and in particular K0G as well, satisfy finite assembly. And the image of the map that we're interested in, this image of the map in reduced K-theory, is equal to just the finite part of the Whitehead spectrum. And on the right-hand side, you automatically get K0 of the rational grouping reduced. So now we're left to understand what this Whitehead spectrum is on basically finite subgroups and what this natural map here is. So I hope I'm good. Yeah, I still have some time. This is good. So there's a notion that works in spectra, which is called the Postnikov truncation. So if I have any spectrum, there always, for any n, there's a universal map to something called tau less or equal to n of x, which is also called the Postnikov truncation of x. Which is the idea is basically to kill off all homotopy groups in degree larger than n. And you can do this sort of formally by saying that the mapping spectra have to be an equivalence for any y, or the mapping spaces rather, sorry, not the entire spectrum, but the mapping spaces for any y that has exactly this property that homotopy groups vanish in degree n+1 and so on. And so this is a nice spectrum that has the property that in lower degrees the homotopy groups agree, in higher degrees it vanishes. So when I'm saying this, this is on the infinity category level, this is a nice functor. Since it has this property, well, this universal property, let me come back to what we're interested in, which is, well, we already know that on case 0 for finite groups, this map is 0, right? Now, if we look at the entire natural transformation between those functors, well, once we truncate down to 0, remember, this now only has information in 2 degrees, in 0 and -1. This only has information in degree 0. And moreover, we know that on components, if I just take the 0th homotopy groups, this is a 0 well, this natural transformation has that on the objects, the component is always 0. Therefore, it has to factor through degree -1. Because basically that's what this universal property tells you. Okay. In particular, come on, sorry about that. If you look at this image of this map, so we already reduced it to assembly over the finite subgroup over the white spectrum. Now I only have it in degree -1. So I can reduce this question here to this funny looking co-limit over Allen Lane spectra. They're shifted down by 1 degree, but it's not that bad. And basically, this is all that we're interested in. Okay, and now in the last, okay, I think I should leave about 10 minutes for questions, right?
Yeah, that's great.
Okay, good. Then I'll just state my main theorems of this, and then we can go into this. So one lemma that is, you know, if you go back to Carter's papers on negative K theory of finite groups, you can actually read this off if you sort of are able to translate this into the language of spectra. And this is that this map here for a finite group is just given by a sum of Bockstedt homomorphisms. So the Bockstedt homomorphism is, so if you have the map of this exact sequence that defines the Allen-Lane spectrum of set mod 2, since this is a fiber sequence of spectra, there's a natural connecting map. And this is exactly the Bockstedt homomorphism. Yeah, so basically for each of those irreducible representations, you have a split that have this weird true index condition. You have a split summand sitting inside here, and it's exactly hit by 1 component in this negative K-theory group. Yeah, and so, and this only happens for the prime 2. And so if we localize away from this, then, well, this map is 0, and whoops. I'm sorry. My fingers are getting sweaty. Yeah. So if we localize away from 2 at any prime, this map will, that natural transformation will be 0. That in itself is not sufficient to show that the entire natural transformation is the 0 transformation, but in this case, this works out because the rest of the groups involved are all 3. So there's a little bit more work to do, but fundamentally what I've shown is that the image of this group is always a 2 torsion subgroup. Okay, well, we were hoping it was trivial because that's what happened in the final case, but at least we have some bound on how bad this is. And we can make this a bit more precise. And so suppose tree satisfies the Farrell-Jones conjecture, and it furthermore has a model of the classifying space for finite subgroups. So this is a tree space that always exists for any group. And sometimes you can give a geometric description of it. But the point is that if I have the assumption that all 0 and 1 cells have this property that this Schur index condition vanishes for all of the isotropy groups, then this map is trivial. So this is a mouthful, but in particular, if I have that all finite subgroups satisfy this condition, then in particular the classifying space does it. So for example, if G is abelian, or if I know that for some reason all the subgroups involved are symmetric or dihedral, have some condition, then I know that this map is trivial. So as an example, I've given this before. What's going on here? Oops. So if I look at SL2 over the integers, the sort of one case that I was interested in the beginning, then this has a nice description as a group in terms of you have the C4 and the C6 sitting inside it, and it's actually given as a free product over the subgroup C2. And using this, you know that all the finite subgroups have to form either a C4 or a C2 or a C6. And all of them have the property, that means they're abelian. So all of them have the property that S of H is equal to 0. So in particular for this group, I know that this map is trivial. Okay, that's already got cool. But there was a reason why I struggled so much with proving this entire theorem, which is it's not come on, it's just getting weird. Okay. There are groups that have a non-trivial map in reduced K theory here. And one of the earliest, the smallest examples you can find is if you take basically the group Q16 as a base, and this is a degree 2 extension of this group, as in it contains Q16 as a degree 2 subgroup, which is normal, of course. Oh. Sorry about that. I wish this would go smoother. Okay, and it says I'm just giving here the presentation as a group here. It's sort of, this QD is also called quasi-dihedral group, which is sort of in between a quaternionic and also a dihedral group, as in you have this conjugation property here, and for the quaternionic groups, this would be an A to the 15, and for the dihedral groups, it would be A inverse. Wait. No, that's not quite true. Yeah, so for the dihedral group, it would be A to the 15, and for the quaternionic group, you would have that this B has B to the 4 is equal to 1, not B squared is equal to 1. And this is sort of A to the 7 instead of A to the 15. But anyhow, this group contains Q16, and I mean, this is sort of a little bit of fooling around with the algebra, and has the fundamental property of it is that its negative K0 vanishes. So this is 0, but for Q16 we get a set mod 2, and basically the fact that this map on negative K theory is not injective gives you some connecting homomorphism if you use the right models, and this from this you can then sort of calculate that this is the case. Okay, I prepared some more stuff for those that have questions to the proof, but for now, thanks for your attention.
Okay, great. On behalf of everyone, I'd like to thank Georg. Are there any questions?
Yeah, I have a question. Oh, sorry.
No, please go ahead.
Okay. Well, I have a question. So there's another map that looks a bit like yours, but it's from K0 to HH0, and it's related to a conjecture of Bass. And I wonder if your result actually gives some information about that map.
So I've been thinking about this a little bit with my colleagues, and sort of the result. What we think is true is that all of those phenomena of this kind of weird two torsion subgroups appearing will disappear when you go to HH. Sort of the reason being that once you go to HH, you always, I mean, it's always,
it's always free, right? On the
yeah, it's always free, and so this is sort of this trace map behaves sort of like an Euler characteristic, but yeah, I don't have a precise result, but I've been thinking about this for a while, and I will think about this a bit more.
Okay.
Hopefully, I can come back to you when I figure it out. But yeah,
but it seems to imply that if it's two torsion, then it seems to imply that the map has to be 0, which would prove this conjecture of Bass, which would be really nice. But okay, if you're thinking about it, then
yeah,
I can't wait to hear more about it. Thank you. It was a nice talk, by the way. Thank you.
Thanks.
Hi, George. Thank you for your talk. I wanted to ask you the following question. So during your talk, you defined a couple of functors from the orbit category of G to spectra. Do any or all of these extend to functors from the Burnside category of G to spectra? Like, do they define spectral Mackey functors?
For finite groups, I think this has been worked out. In my case, it sort of doesn't, it's not really relevant because the finite groups are the trivial case for me. But yeah, there's Mona Melling has written a PhD thesis on spectral, like on giving a genuine equivariant structure on K-theory. And there's also Barwick's approach. But the caveat always is that you work with finite or pro-finite groups, because otherwise there's not really a good notion of equivariant kind of spectra yet. But I assume that something like this should be work in general. Just playing around with this a lot, and you get the feeling that this should work for more general groups. But I don't know yet. Of course, there has to be some restriction, because you cannot. This kind of Burnside category then would be some kind of span category, but you only allow like certain maps in one direction, which would be like finite index inclusion, I think. And then it should be true that this works out, but sadly we don't have a good notion of equivariant spectra yet for this case.
I see. Yeah. All right. Yeah. Thank you. Great.
I guess I wanted to kind of figure out how you came across these counterexamples. Like, what kind of techniques were you using to like find this like really big?
So I said in one side remark that I computed this negative K theory for all groups less than 100, right? So what I basically did, I wrote a bit of code to let gap run through all groups of a certain size. And then I noticed that, you know, I mean, only those certain groups appeared, and was wondering if there was a counterexample to this kind of like my conjecture originally was, and I actually at some stage I wrote to my professor that I know I have a proof for this, and then I tried to write down the exact proof and I just couldn't do it. So I ran for those counterexamples and was thinking like, how could this work? And my idea was that I have to have basically I want to go into I would want to go into this if I had enough time. But I just looked at dihedral sort of virtual cyclic groups sitting over the infinite dihedral group, and for those I have a nice model of the classifying space, which sort of looks like this. It looks all of those groups have to basically the reals as their classifying space sort of glued together in this funny way here. And for those I have a nice property of describing so both negative K-theory of the integral grouping as well as the rational K-theory in degree 0 as some push out. And so I was thinking if I had that the subgroup, the index 2 subgroups had negative K-theory and 2 torsion in it, but the bigger group doesn't, then maybe I could show that it doesn't, that this will be naturally mapped into into K-theory of the rationals. Of course, I'm skimming over some details here, but like I was just playing around with those diagrams for a long time, and I thought like that's the only way I can make it happen, and that's why I tried this out. And there's nothing particularly unique about this QD32. There's a bunch of other groups that also works. I think Q16 has like 5 natural. Okay, bye. Has some like 5 natural extensions into like it sits into 5 different degree 32 groups, and like I think 3 of them work. Yeah, and then as you get bigger, I don't know, it becomes a bit more unwieldy. But in essence, you only need to understand the map on K-1, and you need to understand a little bit about the rational representation. But you can do it with character tables. Yeah, so there's no deeper reason as I understand yet, but it's just playing around a little bit with this.
Cool, thank you.
All right.
Are there any other questions for Georg?
Just make this big because I was talking about it. I don't know what's going on here. This is now a question to the audience. Do you have a good app on iPads that you use for talks like this? Because GoodNotes is great, but exactly this problem of trying to hide some text and then making it bigger doesn't seem to work that well.
Yeah, I've seen, I guess I can